Circular and reciprocal functions. Now we are back to trigonometry, and just quickly, if I have a circle and circular movement, if I take any point on the circle, I can talk about its position in respect with what is its y value and what is its x value. If I have that x and y value, we can refer to that distance because as I move along this circle, my x value will get starting to get bigger, and my y value, which was a maximum here, my x value, which was a maximum here, will get smaller as I go further and further. This x value will get smaller and smaller, and my y value will get bigger until it gets there. Then my y value will get smaller. So this distance here will get smaller as I go along, and my x value, which is this reading, this distance will get longer and longer as I go around my circle. So it starts repeating itself until I get back here. Now this position, where I describe the position by using its position on a circle, is called circular functions. And because we have right angles, we can refer to this using trigonometry. So we can say this is theta, this is my y value, this is my x value, and this is my ratios, or this is my radius r. Now we've done a lot of this in previously in other grades, so you should know the sine, cos, and tan function. We can explain in any position. We also do it in vector maths, where we say position has got something to do with the x and y position. What we're going to get to now is we didn't teach you everything. We said that the sine of any angle, the sine of theta, is the relationship between the y over the radius. So the opposite side over the hypotenuse of that right angle triangle is called the sine ratio. So the sine of that. So why is this important? Well, if I take and I start with 0 degrees, and I find out what is the ratio, then it is y over r. The y will be 0 when this is a straight line, and r will be a maximum. Alright, so then y over r is 0, and we get our first value. And if I draw that in the graph, it's 0. If I go to 1 degrees, then this y will get a little bit bigger, and r will stay the same. And if I plot all those points for 360 degrees, it starts looking like that. If I plot all those points. Okay, and that is then how the graph would look for every point that's on the outside of this. If I look at the sine, for example, the ratio of the opposite side over the radius. Now, this graph we find a lot in physics. So in all sound graphs, for example, we find this, and this becomes very helpful when I try to imitate sounds and things in physics. So it's a really real life application in a lot of our other subjects. So how do I do this then? Well, this is why we do it, because we can relate this to physics, and we can use that to find out where position is going to be with all these periodic functions. Because what's happening is this will repeat itself over and over. As this point moves around and around and around, this thing will keep on repeating itself. And that's why it's called periodic functions, because it happens in certain periods and it just repeats itself. Now, we said that sine theta is y over x. If we look at the next function, which is the cos, it's actually the cosine function. It's cosine. Then we have the tangent. Now, this is what you've learned before. Now, if I have sine, cos, and tan, which is, in this case, just looking at that, sine is y over r, opposite over hypotenuse. Cos will be the closest, which is x over r. And then tangent will be the opposite over the adjacent, which is y over x. What you haven't done up to now is if we look at the reciprocal function. So the reciprocal is if I turn this around. If I turn this around, I will get y over x, and that is called the cotan. And we just say cot. So we say cot theta, which is then x over y. R over x is the reciprocal function of cos, and that's called the secant function, and that is r over x. And if I turn y over r around, which is the reciprocal of that, we get the co-function, which is the cosecant, cosec of theta, and that is y over r. So what we have is that the sine is the sine is the reciprocal function. Cos is the cosec is the reciprocal function of sine. Sec is the reciprocal function of cos, and cot and tan are reciprocal functions. But we've got another important thing as well. We've got the sine theta and the cosine theta, the tan of theta, the cotan of theta, the sec of theta and the cosec of theta. They are co-functions. Now, if you can remember correctly from year 8, year 9 geometry, we talked about complementary angles. Now, complementary angle is an angle that makes 90 degrees. Okay, so if I have the theta and I work from the y-axis, I'm just going to enlarge that a little bit. So if we say this is theta, then this will be 90 degrees minus theta. And I use this quadrant to show this because it's the easiest way to do it. It's a little bit harder when I work from the other complementary angles, but the principle is the same. So if this is y, this is x, and this is r, I can see that the sine of theta is y over r. Cos of theta, x over r. Tan of theta, r over x. Y over x. If I ask what's it for 90 over theta, it means I'm going to complete my triangle in this direction, which means this is x and this is y, and this is now my angle. So which means the sinus of 90 degrees minus theta equals, and if I work from 90 minus theta, sine is opposite over hypotenuse, so that's x over r. And cos of 90 degrees minus theta equals y over r. And then the tan of theta of 90 degrees minus theta equals, the tan is opposite over hypotenuse, which is x over y. So what we see now is that 90 minus theta is the same as the cos of theta because they are complementary angles. So sine 90 minus theta, working from the 90, the cosine equals the sine, and the sine equals the cosine of the complementary angle. So when I work from the 90 degrees, sine changed to cosine and cos changed to sine. What happens with tan? Well, tan is y over x, right? And if we look at this, tan is y over x. So what's the co-function of tan? It's cotan, x over y. So look what happens. The tan of 90 minus theta equals, the cot of 90 minus theta equals the cot of theta. So when I work from my 90 degrees, or from my 270, so 90 plus theta, 90 minus theta, my co-functions change. My function changed to my cos, and my cos changed to sine, tan to cot, cot to tan, and sec to cosec, and co to sec. We also have done in year 11 Maths B, we looked at working from 180. So what we said is if I look at this position, the ratio of y over x in this case here, the ratio of y over x, if this is theta and this is also theta, is exactly the same because this is the same, this is the same. The only thing that changes is that this is now minus x. So if I look at sine, the sine will stay exactly the same. Y over x is the same as y over x. And this is why, that's where we get our cast diagram from. So our cast diagram said that, and I'm not going to go through all of that, our cast diagram said that in my first quadrant everything is positive because y and x positive. In my second quadrant, sine is positive. Now with sine, if sine is positive because y over r is positive, which means that the cosec will also be positive because that's r over y, and y is positive in my second quadrant. So my cast diagram apply for sine as well as the reciprocal function. In my third quadrant, tan was positive, and the reason because that is, if I come down in this direction, this is now minus y, it's the same size as y, and I can always refer it back to my reference angle in my first quadrant. This is minus y, this is minus x. So minus y over r will be negative, minus x over r will be negative. The only thing that will be positive is opposite over hypotenuse, and that is tan. Because it's negative divided by negative, tan will be positive, and that's why tan is here. So the moment I have y and x, it is positive in my third quadrant, and that is why cot is also positive. So the cast diagram applies for your reciprocal functions. If you look at the examples, you'll see we're going to just use that. If I work from my x-axis, we are changing always to my reference angle, which is the first. The only thing that changes the signs. And if I work then from my y-axis, we always change to complementary angles before we go to the reference angle. If I can have a quick look then, in my first quadrant, sine theta, cos theta, tan theta stays like it. Here, sinus theta, sinus of 90 degrees minus theta will become the same as the cos, because I'm working for my 90 degrees, that becomes cos theta. Cos 90 degrees minus theta becomes the tan of the, the sine of theta, but that's negative, sorry, that's plus and plus.